Every household in the United States receives water through a system that was largely engineered in the 19th century. Municipal treatment plants draw from rivers, reservoirs, or underground aquifers, filter and chemically treat the water, then push it through hundreds of miles of pressurized pipe until it reaches a tap. Most people interact with this infrastructure the same way they interact with electricity. They expect it to work, they never think about where it comes from, and they notice it only when it stops. A family of 4 uses roughly 300 gallons per day. Showers, toilets, dishwashers, laundry, drinking, cooking. Water is so embedded in daily routine that it rarely surfaces as a concern, until it does. Think about the last time you turned on a faucet and actually thought about where that water came from. Most people never do. It arrives, it drains, the bill comes at the end of the month, and the cycle repeats. For the majority of American households, water is the one utility that has never felt fragile. Electricity goes out in a storm, gas prices spike, but water has always just been there. That assumption is what makes the shift, when it happens, so disorienting. A sputtering tap, a boil water notice, a utility letter about mandatory conservation. Small interruptions that most people file away and forget. But for households in the Western United States, those interruptions have been arriving with increasing frequency, and the infrastructure behind them is under pressures that were not part of the original design. The friction in this system is less visible than it used to be, but it is measurable and well documented. The Ogallala Aquifer, which sits beneath 8 states in the American Great Plains and provides irrigation and drinking water for millions of people, has been declining for decades. In some regions, its depth has dropped by more than 100 feet since large-scale extraction began. Lake Mead, the largest surface reservoir in the country by volume, reached historically low levels in the early 2020s, triggering federally mandated cuts to water allocations across the Southwest. These are not edge cases. They are ongoing structural pressures on a water delivery system that was not designed for the climate conditions or population distribution that now define the country. Drought cycles that once measured in months are now measured in years, and hydrologists refer to some of what is unfolding in the western United States as a mega-drought, a term that describes prolonged, regionally widespread water deficit rather than a single dry season. For most people, the response to this backdrop is to do nothing differently. Municipal water service continues in most places, and bottled water fills the gap when trust in tap quality erodes. Larger-scale alternatives do exist: whole home filtration, rainwater harvesting, private wells, and commercially manufactured atmospheric water generators. Each of these involves real trade-offs. A private well requires drilling, permitting, and ongoing pump maintenance, with costs that typically run between $5,000 and $15,000 before water flows. Rainwater harvesting depends on precipitation, which is precisely what fails during extended drought. Commercial atmospheric water generators, machines that extract humidity from ambient air and condense it into drinkable water, have been available for several decades, primarily in military and industrial applications, and now increasingly in consumer form. Units capable of producing meaningful daily output are generally priced between $3,000 and $10,000 depending on capacity and filtration quality, which places them outside the budget of most households. Within this landscape, a digital product called Joseph's Well occupies a specific position. It is a DIY construction guide centered on building a home-scale atmospheric water generator using components sourced from consumer hardware stores. The guide is designed for people who want to construct a functional water collection system themselves rather than purchase a finished commercial unit. Joseph's Well is a digital product, not a physical device. When a buyer completes a purchase through the product's distribution platform, they receive immediate access to a set of downloadable and streamable materials. These include a step-by-step video guide that walks through the full build process, printable blueprints and schematics that show how the components fit together, a materials list with sourcing information, and separate instructions for wiring the system either to a standard electrical outlet or to an off-grid solar configuration using a car battery and a small solar panel. 3 supplementary guides are also included covering water storage practices, purification and remineralization techniques, and a breakdown of common contaminants found in municipal tap water. Ongoing email access to the guide's author is offered as part of the package. The build process the guide describes begins with sourcing components, primarily the kind of refrigeration and dehumidification hardware found in consumer appliances, a dehumidifier, a condensing coil, wiring, a collection vessel, and filtration materials are the core elements. The video guide walks through disassembly of donor appliances, reassembly into the target configuration, and the connection of the condensing cycle that pulls ambient moisture from the air, chills it until it condenses into liquid, and channels that liquid through a filtration stage before collecting it in a tank. The builder handles physical components with standard hand tools, screwdrivers, wire connectors, basic plumbing fittings. No specialized fabrication equipment is required. The guide estimates the total parts cost at under $150 and positions the system as something a person without an engineering background can complete in a single day following the video instructions. Once built, the system is designed to operate continuously or on demand with minimal intervention. The guide describes it as a low-maintenance setup. The primary ongoing requirement is cleaning the collection tank and replacing filtration media at intervals, similar to maintaining any home water filtration product. Output volume depends on ambient humidity, which is a meaningful variable. Atmospheric water generation becomes less productive in very dry, low-humidity environments. The guide's stated output figure of up to 50 gallons per day reflects high humidity conditions. In arid climates, the desert regions where water stress is most acute, daily yields are likely to be considerably lower, though the guide does address regional variability and adjustments. The system runs on standard household current, drawing roughly the same power load as a small appliance, or on a solar configuration for off-grid operation. The product is most naturally aligned with people who have some comfort with hands-on projects, access to basic tools, and a specific interest in reducing dependence on municipal or well-based water infrastructure. It may appeal to households in water-stressed regions, those with existing off-grid setups or solar infrastructure, and people who prefer building systems over purchasing finished products. It is less suited to people who want a plug-and-play solution, those who live in low-humidity climates and need reliable high-volume output, or those without the time or inclination to follow a multi-step construction process. It is a guide to building something, not a thing in itself, and the distinction matters for setting expectations. Compared with purchasing a commercial atmospheric water generator, the primary trade-off is build time and assembly effort in exchange for a substantially lower upfront cost. A commercial unit arrives calibrated, warranted, and serviceable by a manufacturer. A homemade system depends on the quality of the builder's assembly and their ability to troubleshoot. Compared with a whole home filtration system or a private well, the atmospheric approach draws from a different source entirely, the air rather than ground or surface water, which has practical implications in drought conditions where ground sources may be depleted but atmospheric humidity remains available. Compared with bottled water or reliance on municipal supply, it represents a shift toward household-level production rather than consumption from an external supplier. Joseph's Well is, at its core, a set of instructions for building a specific type of water collection device from consumer-grade components, delivered digitally and priced below the cost of a single commercial unit of comparable function. The build centers on atmospheric condensation, a well-understood physical process applied at a household scale through accessible hardware. The question that sits at the edge of this system, and that only someone who has built it can answer with confidence, is whether the output volume achievable in a given household's climate and humidity conditions actually meets that household's practical daily water needs.